say what we will do. I'll quickly introduce myself. Introduce already. I also will introduce our school a little bit. Then I will talk about the basic algorithms and basics of quantum computing, right? And then I will talk about the hardware part. The whole purpose is that to let you know, let you to have an approximate idea on what quantum computer is about. People always think that it's so fancy. It's going to solve all the difficult problems in the world in the future. So is it true? So we can discuss a little bit. I will be quick, right? San Jose State, you might know about this already. It's a small campus, but we have a lot of students, 36,000 students, a very small campus. And we are minority serving institutes. In our E department, we have about 300 master students and 500 undergraduate students. So in our master program, we introduce a specialization on quantum computing. Why is it relevant to you? Actually, I just want to tell you, it's nothing fancy. It's just traditional electrical engineering. First, programming. Programming is nothing. Many of you know Python programming. If you know Python programming, you can control quantum computer nowadays again. Just go to IBM Q, register a free account, submit your job. Then you really have run a quantum computer on the real quantum computer to do some experiments. This one, you may know what I'm talking about. This class is about electrical circuit. Then how electrical circuit is related to quantum computer? Because now the quantum computer need to go to very low temperature. Very low. Like, have you learned about the unit of temperature? What is that?
Kelvin.
Kelvin. Very good, right? So what is the lowest temperature you can achieve? Zero. So what is the vaporization or liquefied temperature of or boiling point of liquid helium? Do you know?
373.
Liquid helium.
Or helium.
Yeah. Very low, like 4 Kelvin. Yeah. So it's low, 4 Kelvin above the absolute zero. But if you want to operate a quantum computer, you need 0.01 Kelvin. So very cool, a very low temperature, lower than the temperature in the space. Okay. So how are you going to operate the electronics in this low temperature, right? When you buy a car, right, or your cell phone, they may say, okay, it still works if you go to Alaska during the winter. That might be just maybe 200 Kelvin. I don't know the exact number, 250 Kelvin, maybe, right? Negative 50 degrees C, for example, right? But now you need to make this electronics work at 0.1 Kelvin, right? Now we cannot do that actually, but ideally, we want to do that. You will know later why, right? And some electromagnetic wave simulation. So in this process, yeah, we teach some quantum computing things, but most of them are electrical engineering. So if some of you are very interested in engineering, actually quantum computing is actually very suitable for engineer. From low temperature engineering, vacuum engineering, to high-speed electronics engineering, and other types of engineering. You will see later why. Right? I will also have a Master of Science in Quantum Technology that we collaborated with the physics department. Okay. And I advertise myself. I have some YouTube video on quantum computing. You can try to get it. And here and all those things. And I also have a book on quantum computing. I don't know, you can request your principal to buy one in your library. Okay, so let's talk about the quantum computing. First of all, why quantum computing, right? The most important thing is that it uses two things. You might not understand what I'm talking about today. I just have something want you to take home. And then if you're interested, you can continue to explore. So why quantum computer is powerful? Because it uses two important theories. One is superposition, one is entanglement. Probably you know what is superposition, right? Anyone know what is superposition? Yeah. Just shut up, yeah.
Yeah, basically basically, for example, let me give you an example. You have a coin, right? You spin it, there's head and tails. In this spinning state, it's superposition because it's between zeros and one. You're thinking head and tails because you don't know.
Okay, there's a good analogy which I'm going to use. Yes, and do you have other idea?
I was gonna use like a
Okay, good. But have you learned about wave, water wave?
Yeah.
Water wave, you always will say, I have a source here, have another source here, and then you have this ripple going out, and eventually they hit each other. And then what is the vibration at where they hit is a superposition of these two water waves, right? So that is a concept of superposition. But like we will talk about what they try to compare also later, right? So superposition, you actually learn this in wave mechanics. Entanglement, we will talk about that later. One important thing is about interference. This also related to the water wave I just mentioned. If you read, some of you might have learned about destructive and constructive interference, right? You have two sources, they enhance the result together, or destructive, right? This is important for measurement, right? So another important thing is there are two types of quantum computer when people talk about it. One is the gate-based model. Gate-based is just like your classical computer. You may have an AND gate, NOR gate, but of course it doesn't use AND gate and NOR gate, right? Logic gate, right? And or not, all this operation. But it's based on the gate, like here, right? You have some gate, NOT gate, Hadamard gate, or identity gate. That this require very high accuracy. You cannot have error. This is just like an analog computing. So if you have error, they will accumulate. And that is nowadays problem. Now we still don't have something called error-corrected quantum computer. So as a result, it doesn't work most of the time. Another thing, so this is like Google, IBM, they all use this gate-based. Quantum annealing is another type of quantum computer, right? What they do is just use some quantum mechanics to map to a real problem. And then you try to find the lowest energy of that system. And one way to think about that is that you have a lot of ball, right, on a landscape. They're everywhere. So you try to vibrate it so that eventually they all go to the lowest position. That is the minimal energy they can gain, right? And if you can map this physical problem to a real problem, what type of problem? For example, material and drug design, or logistic problem. Like, so nowadays when you ask those quantum computer companies, who are their customers, you'll find that it's very interesting. One is the pharmaceutical company, because they need to design drug. If they can find the protein, the right drug faster than the competitor, they will grab the whole market. What else? The car manufacturing company. How come car is related to quantum computing? Because they care about the logistics. How should they locate all the dealer in different city? How should they transport their different parts of the car to different city so that they minimize the overall maintenance cost and maximize the number of customers? That's a billion-dollar problem. Another type of customer what? The financial customer. Wells Fargo has a team working on quantum computer. I don't know if you know. What are they doing? Probably two things. One is you heard about quantum computing can break nowadays cryptography, right? So all the banking transaction you are doing now is based on some special cryptography algorithm that you, in principle, you can break it, but it takes maybe thousands or millions of years using a supercomputer. So you can break all the password we type in today. But using quantum computer, there's a promise that a kind of promise that we can break it in a few seconds if it is successful, right? So, and what else? Investment, right? You know that every day Wall Street, Dow Jones Index go up and down. By 1%, all these people play with margin, leverage. And if they can find out, predict what happened to the stock market 1 second earlier than their competitor, they will earn maybe 1 billion more. And that's why all these financial companies, they invest in quantum computing. So it is pretty interesting, right? So let's spend some time. I have quite some slides, but I think we spend more time on the first few slides will be good, right? Not everyone know about classical computer, but anyway, let's take it for granted. Classical computer is nothing, it's just to process our daily information. They try to make our data all into the binary numbers 0 and 1. Right? For example, even for my name, my last name, W, Wong, right? W, it has ASCII code. if you go to a computer, it corresponds to a certain code. I don't know what is the number, let's say 100. Then you convert 100 to binary number. And these are the numbers saved in this computer, right? Like in the, maybe in Charlie's calendar, say today there's a talk by WONG, and this W is saved in this way, right? So everything is related, represent in 0 and 1. How do we represent 0 and 1? They just mentioned use the coin, right? There are many ways to do that, you are right. Use the coin head and tail. If I just put the coin in the right orientation, I ask you what is this alphabet, you just decode it, you say, okay, this is W. That is easy, right? Well, not necessary coin. Happy and sad is also okay. Anything that is binary, contradictory to each other, even this table, upside down or not upside down, is a representation of the information. Right? But in our computer, of course, we use something called switch, which is transistor on and off, just like the switch on the wall, right? But they are so tiny, so fast. Nowadays, Intel, for one chip, they have about I think maybe even close to 10 billions of transistors in a few centimeters square. That is really amazing. That is the most beautiful artwork and engineering work the human can have. 10 billions of transistors, none of them are not working. Everyone is working as they are supposed to be. Think about that, 10 billion. So we use 0 and 1 to represent information. Then one is quantum computing. Quantum computing, although look fancy, but it is the same as classical if we only allow them to operate in 0 and 1. So in some sense, I put in something called direct bracket notation. You don't need to worry about this. But if you see this, don't worry. Now, that is one thing I want to share with you. When you read something new, usually you are scared of it. You're scared of something because you're not familiar with that thing. So if you need to learn something, you look at the paper, so many equations, I don't know what it is talking about. Usually we are scared, we give up. Now, unless you need to take an exam the next day, there's no point to be scared. Or my professor told me that all you need to do, just keep reading, and you get familiar with that, then you won't be scared. Then you will be able to understand it slowly, right? Same for this one, you trust me, I'm telling you this is nothing special, it's just treat it as a symbol. It's nothing different from here, although it's a very profound notation invented by Dirac, which is a genius in quantum mechanics. He proposed many useful things. This is a very useful notation. But at this stage, just take it for granted. Although at the beginning you feel so uncomfortable, is this parenthesis? Can I add it? Can I do multiplication? Right? But anyway, we can represent the state in a quantum computer by this, just the basic state. So again, I can have an on and off. If I say, hey, quantum computer, you only can operate using this state, then they are no difference from a classical computer. We call this the basis state. Okay, so what is basis state? Again, this is just an analogy, and do not use it too far. Just like your Cartesian coordinate. You have learned vector, I believe, right? So for every vector in your 2D plane, we can represent it as, let's say, 3x hat plus 4y hat, or 3 units of x plus 5 units of y. What is x and y actually? If you ask yourself, you actually don't know. No one tell me what is x and y. Oh, okay, from the figure, I know that it is, right?
It's kind of deep.
Yeah,
Oh,
over there.
okay, right? So, when you have a vector here, you say, okay, this one is 3 units, this is 4 units. But what do you mean 4 of what? I know it's 4. 4 of what? You probably say that, hey, 4 of this length and 3 of this length, right? So these are the basis vector. But actually, we did not really care about what is this length. We just say this is the basis. So same for this one, right? So these are the basis vector. So when I say this, you already see this is a superposition because this vector, I can write it as V equals to, let me just say it, V equal to 3x plus 4y. Right? But you know that when I say x, I mean x hat, right? 3 unit of x, right? So, okay. So now, if you agree that on my 2D plane, I have this unit vector, I have this superposition, why don't you agree that there's also a space which we cannot touch? I'm not talking about scientific fiction. It's just a mathematical space. I also may have the unit vector or the basis. And as a result, the vector in the space can be a superposition. Here I'm trying to do superposition. This vector equal to alpha times 0 plus beta times 1. Right? If you still feel this is very confusing, then why don't you think about this equal to psi equal to alpha of x hat plus beta of y hat? Would this make you feel more comfortable? Because this is what you have been using in your algebra, right? In your when you learn the coordinate. So what I have changed is just change x hat to 0 and y hat to 1 is just a notation. You know, I can even say alpha orange plus beta apple if I want. But this is two-hand waving because there's some mathematical relationship between them. Because x is orthogonal to y. In your 2D plane, they're perpendicular to each other. But is orange orthogonal to apple? Might not, right? So just an analogy. So if you don't understand something well, but you are interested in that, swallow it for now. And later, you can learn linear algebra to get a better understanding, right? And that's why you need teacher, right? I don't think you understand everything your teacher taught you. If you try to spend your time to understand everything, it will take more than 10 years, right? I always say that in elementary school, they taught you how to do division and multiplication. Have you ever tried to prove that what they are telling you is correct? You never, right? Until maybe in the college or one day you're good enough, you suddenly realize, hey, that is correct. That has some basic there, right? Same for here, and that's why you need teacher. You trust them for now, but you need proof later. So similarly, just in extreme case like what they said, if the head and tail are the basis states, I can also have a superposition of the head and tail. And one way to think about that, this is not a real quantum computer. I like spinning a coin on the table. Is it head or tail? No, I don't know, right? Because it's spinning. I don't know whether it's head or tail. But this is, again, an analogy, right? You cannot build a quantum computer by spinning the coins on the table, right? So the main point here I want to tell you is that superposition, which is a linear combination, right, of the basis state, give you the power of quantum computer. Why is that? Any questions so far? Again, it's yeah. Anyway. Let's think about classical register. If you're not familiar with binary number, you just try to feel what I'm saying. You don't need to understand everything. In a classical register, if you have 4 qubits, right? I have 4 coins represent the information. I can have up and down, right? So I can have 0. So how many number can I represent? I can represent 0, 0, 0, 0. I have 4 coins, right? Head, 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 head. And then that represent one piece of information. It can be W, right? And then 0, 0, 1. Or 0, 0, 1, 0. Correct? So because each of them has two possibilities. So the total possibility of this one is 16. Make sense? 2 to the power 4. If I have 4 coins, I have so much, right, information. Now, how about in quantum computer? As I told you, if I only allow these basis states to operate, I only also can represent 16 basis states. It's just like earlier, I have 0 and 1, and head and tail, right, is the same in classical and quantum computing, right? But what is so powerful about quantum computing is due to quantum mechanics. You actually can have a superposition of these 16 basis states. Maybe let me emphasize, maybe I'm too far. When you have only one, what we call one qubit, or one state, you can only have 0 and 1. And if you have 2 qubit, what state can you represent? 0, 0, 0, 1, 1, 0. Yeah. 1, 1, good, okay. And how about you have 3 qubit? 0, 0, 8 of that. Yeah, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then 1, 0, 0, 1, 1, just 8 of that, right? It is 2 to the power 3. If I have n qubits, like in 4 qubits are 2 to the power 4 basis states, right? So if I have n qubits, because quantum computing allows something to exist in superposition, so I can have the linear combination of all of them. For the linear combination for each basis state, I need one compressed number to describe it. Right? If we go back to here, for only 1 qubit, I have 2 to the power 1 basis state. I need 2 compressed number, 2 number, alpha and beta. And this is a compressed number. This is not just real number. So it means that if I have n qubit, I need 2 to the power n. It just goes up exponentially. Think about if I have 300 electrons, 300 qubits. How many compressed number do I need to describe? 2 to the power 300. Maybe you think it's very small, right? But probably many of you don't think so already. You have tried that before, and your calculator just blew up, right? If I have 300 electrons, it means I need 10 to the power 90 compressed number. 2 to the 300, like 2 to the power 90. Do you know how many atoms we have in the universe? Only 10 to the power 82. How many megabytes, how many bytes of memory we have in the Earth, on the Earth right now, including this computer? Less than 10 to the power 21 bytes. So here is not showing the power of quantum computing yet, but it shows the profound information you have when you represent a state as a superposition of the basis state. It grew up so far. For 1 qubit, only 2. 2 qubit, I have 4 compressed number. And for 300, which even a kindergartner might be able to count it from 1 to 300, it go up to 2 to the power 10 to the power 90. You even cannot describe by the atom. If you try to store every number in one atom, let's say you can do it. You even cannot store the state of 300 electrons. Use all the atoms, including your body, in the universe. So it's very profound. It means that if you can garner this power, you probably can do something very powerful, right? So that is the superposition. Superposition means that it allows you to have a state of a system in a linear combination of the basis state, okay? But what does it mean? Actually, I should have a better picture. There was a movie called Anywhere, Anytime. What was that? Everywhere, I forgot the name. The one that got the Oscar. Everywhere, every time, all at once.
Yeah.
Everything, everywhere, all at once.
Everywhere, all at once. Yeah. That is actually a multi-universe. All you can think about is quantum mechanics. What does it mean? If we say that I have a state that is a linear combination of the basis state, I apply a function to it. You know what is function? You do calculation, right? Let's say it works. Then isn't that because it's linear combination, I can calculate all of them at the same time. Okay? So it is like that I have a parallel universe. I do all the computation at the same time, right? So this is very philosophical. It's not our problem. The physicists is still trying to understand the meaning of quantum mechanics. What is the meaning that the electron can go to the right and go to the left half at the same time before you detect it, okay? So, but however, this proves one important thing is that all I need to do is just make them as a superposition of the basis state, and then apply a function to it, a machine to calculate it. They can all be calculated at the same time. Isn't that cool? So I can do, if I have 300 electron, looks like I can calculate 2 to the power 300 function all at the same time. It's impossible using classical computer, right? But there are lots of caveats, right? So do not believe people if they say they can do it easily. Before that, we need to understand what is the meaning of measurement. So you do a lot of computation, then tell me the answer. If you cannot tell me the answer, I don't trust that you have done the calculation. Just like I am the richest people in the world. I'm true, I'm not lying to you. I'm richer than Bill Gates. Like, can you prove that I'm wrong? You probably cannot, right? But if I don't bring up the money, right, show you I have a $100 trillion, what is the point? I always can say I'm richer than Bill Gates, right? I'm very rich, last 1 second I want $1 trillion, but I just spent $1 trillion right away to buy a planet outside the universe, right? This is such a far cost computation. You cannot say. Same for quantum computer. I say it contains 2 to the power 300 complex number in that 300 electron. But if I cannot get the answer, what is the point of having that quantum computer? I need to get the answer, right? So how do I get answer? Get answer means measurement. Just like in your lab, when you do a measurement, you actually try to get the answer. But unfortunately, by quantum mechanics, if your coin is spinning, how do you know whether it's up or down? No way, right? Unless you stop it. You stop it, it can be up or it can be down, right? Same for quantum mechanics. If you have a state in a superposition of 0 and 1, and you measure it using any physical method, we say that the wave function, the state, will collapse to either 0 or to 1, randomly, completely randomly, right? That's why Einstein doesn't like quantum mechanics, didn't like quantum mechanics. He said that God doesn't play dice, right? Because he just think that quantum mechanics is great, but something is missing. He doesn't believe in this randomness. But the point is, after almost 100 years, people still cannot prove that this is wrong. And they still cannot find the hidden variable. Einstein said either it's wrong, which he actually did not think so, or there's some hidden variable. We still did not really understand quantum mechanics. But there have been many experiments to show that there's no this hidden variable, including the Nobel Prize that was awarded maybe 2 years ago about this Bell inequality, right? That although that cannot completely prove that, because whenever you do an experiment, there is always a possibility that experiment is not exactly correct due to other factors, right? But anyway, so that is measurement, and that is the reason. How do I get the coefficient? You actually cannot get it. How can you read the coefficient from the state? You only know that the probability that you will collapse to 0 is proportional to the magnitude of the square of the coefficient. For example, if alpha is 0.1, then you have 0.01 chance to measure 0, right? So how can you find the probability of measuring something experimentally? What would you do?
Just do it a lot of times and count it up.
Just do a lot of time, right? Even you do it one time, you don't know what it is. Then it means just to get this coefficient, I might need to do the measurement 100 times. But the problem is once I do one measurement, it changed the state already. That means I need to prepare many identical samples, maybe 100 of them, and keep doing the measurement. Then I can estimate what is the value of alpha and beta. And just now I say that, hey, quantum computing is so cool with superposition. I have all this coefficient. How are you going to get this? You need to do trillions of measurements in order to estimate their value. And that actually slows it down. It becomes useless in that sense. Okay? So we have talked about superposition. Well, superposition make it very profound, right? It can process many things at the same time. But then I tell you about measurement. How do you extract them? If you just use measurement, basically it's useless because you need to do a lot of preparation and measurement. Of course, people come up with something very smart. They will do interference so that there's always only one answer comes out. And based on that answer, they can infer something. Okay? But we won't talk about that. Another important thing is about entanglement. So entanglement, maybe I think I won't go into the math here. But entanglement basically is saying that if you have a two body, they are highly correlated when they are entangled. This is easy to understand, right? My hair are entangled, it means that I cannot separate them easily, right? And if I do something to one of the hair, the other may get affected. For example, I try to burn one of the hair, and then because they're so entangled, it's going to burn another hair, right? I hope you understand the heavily coupled concept about entanglement. We can look at, this is what Einstein called the spooky action. The goal is not to discuss whether this is philosophically what the implication is this. Just to show you the special feature about quantum mechanics. Yes.
Wait, so if two electrons are like in an entangled state with each other, if you measure one of them, then will like the other one get affected?
Yes, that is what I'm going to say. Very good, right? So let's follow what he said. So I have a state, right? I have two electrons. Here, instead of using 0 and 1, I use spin up and spin down. That's a property of the electron. Just take it for granted. The electron has a property called spin. In reality, it's not a spinning of the ball, right? It's just a property, like the charge of an electron is positive, negative. It's negative, right? The charge of particle. And spin is just an intrinsic property of a particle. Just take it for granted. So you can treat this as 0, 0, 1, 1, right? Now, if you feel confused about this, just think about this. I talk about superposition. So this state is a superposition of two basis states. This one plus this one is a superposition. This basis state is 0, 0 plus 1, 1. Because I have two qubits, instead of just alpha 0 plus beta 1, now I have alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1. Right? I can have four coefficients, right? Just like instead of 2D plane, not even 3D, now I live in a 4D space, 4-dimensional space. You cannot feel it, but you agree that it exists. But I don't want to talk about this space, by the way. If sometimes you feel that difficult to understand, you can look back. For example, if you have an ant, the ant can only live on a 2D space. Let's say the Earth is large enough, flat enough, the ant will always walk on the 2D space. And if you talk to the ant, you say, hey, you know this, it is 3D in this universe, you can go up. But it never able to go up, right? So the ants won't be able to understand what you're talking about because it cannot feel the 3D space. But however, you are very confident how to describe a 3D space. And you can teach the ant the math, right? You only have x plus y, 2x plus 3y, right? X hat, y hat. You actually have a z hat also. And similarly, now the alien tell us that there's 4D, 5D, 100D, you don't understand, just extend what you know. Why you only want to confine you in the 3D space. And this so-called 3D space, of course, is not where we live in. It is a hyperspace, abstract space. Right? So here we have a 2D space, two-dimensional space, 0, 0, and 1, 1, right? So this is a superposition. Now let's say I'm very careful. I have a very noiseless channel. And we call this entanglement. When I move one electron all the way to very far away, 100 light years away, I just take time. I have a lot of time. Let's say I'm very long life, 10,000 years old. Right? Wait for one, they move so far, and I do the experiment. So my alien friend is on another planet. Now, if now I try to do a measurement on the Earth, because this whole system still at 0, 0 plus 1, 1, right? I did not disturb it. They already move away, but this is the system, 0, 0 plus 1, 1. If I do measurement, do you remember the wave function will collapse, just like the spinning coin, right? It will collapse to the basis state. But I only have two basis states for this system, up, up, or 0, 0, and 1, 1. So it will only collapse when I measure, I either will get up or down, 50%. The point is, once I measure up, then I know the electron far away will be also spinning up. Now, when I measure it, it takes 100 light years for the light to transmit the information to this planet to tell the electron that I got up. But no, this will get up instantaneously. Yeah.
Wait, but how can it transfer that data instantaneously?
It does not. So that's why Einstein does not like that spooky action at a distance. So it's not because it transmits the information instantaneously faster than the speed of light. But so here has a lot of things we can discuss. People can prove that this does not violate the causality principle, that I'm not going to be able to, let's say, stop my parents by stop their marriage going back to the future, right? So people can prove that. Yeah.
So if you can change like the energy state of the electron using like entanglement, then wouldn't you be transferring like how does that not violate like Einstein's?
It does not transfer any energy. That is the point. So this is the whole system. This is a system, right? And the system only have up, up plus down, down. It only can have these two states. So once I measure this electron, it means the whole system would collapse at the same time to up, up. They just becomes up, up at the same time. How to say? So let's say I have spinning coin, right? I cannot do that in reality, but let's say I make them entangle. So now it's a superposition of both up or both down. Then I move this spinning coin to very far away. I only try to stop the coin spinning in front of me. It becomes head. And what this is saying that coin far away will also just collapse to head, even though no people touch it. That is what is essentially saying. But again, spinning coin is not a real quantum object, right? So you do not talk about information transfer from that point of view. But yeah, so this is like the interesting thing, right? So entangle. But we are not using this. Actually, we do. We use this a lot in quantum algorithm, right? But but we are not trying to discuss whether philosophically what this means. Yeah.
Like you mentioned before that you could use like quantum mechanics for machine learning. Like, are you able to like run a use a transformer architecture on like a quantum computer?
So for machine learning, that is more to speed up the calculation. So when now people talk about quantum machine learning, they actually have two parts. One is the quantum mechanical part, one is the classical part. So they use quantum computer to do some computational intensive calculation. For example, they may use it to do optimization and then go back to the classical computer to do further improvement and then feed back to it. Yeah. So that's how they do it. Yeah. Good questions. Okay, so I don't know if you understand, right? I don't understand. So the point is, you know about this, right? And then if you're interested, you can dig deeper, right? This is something the physicists and philosophers are debating. What is the real meaning? And there's another thing. For example, I bought a pair of gloves from Safeway. Let's say they are only selling blue and red color. And then let's say I'm colorblind. I just open it and then send one of them to my friend in New York. My friend opened the package and see, oh, that is blue. My friend knows immediately, mine is also blue, isn't that? Because he knows the whole process. I'm sending the same color, right? So even before I know what color my glove has, my friend already knows what I have. So a little bit parallel, but not exactly. and there's no transformation of information, right? So what is the meaning of entanglement and coupling, right? My friend knows the color of my glove is, he knows very well our gloves are 100% coupled. They are entangled. If I have red, he has red, right? Yeah.
So basically the two parts of the same system, the two.
Not really dual part. I mean, they both of them form a system, but not of two systems. Yeah. Okay, maybe I talk too much. So let's continue. So we have the state. We know it's powerful because of superposition, and it's strange because of how we do the measurement. It's also powerful because of the entanglement. And then what is quantum computing? Quantum computing is just like you have a physical system. It can can be the spin of electron. It can be the level of an atom, whether it's an excited or ground state or whatever. It has to be a quantum object, right? And what we're doing is that we try to change the vector, just like in the 2D space. We apply something to rotate the vector clockwise, counterclockwise, and eventually we will get our answer. And that is the so-called quantum computing. How do we change, again, how do we change the state of an electron? Think about that, it's a quantum object. Maybe you have not learned that. But in reality, this is like atomic physics. What people do is shoot a laser pulse to it. Then you will go from low state to high state. You shoot the right length, shoot the right frequency, and the right magnitude, right? Then it will change according to what you want. And that is the quantum gate already. So if some of you already learned electrical circuit before, those who are interested in that already know, oh, they are not gate, and then you can form an inverter using transistor, PMOS and NMOS. You might not have learned that, that is fine, but that is a physical one. It's just really like a gate. What transistor you call a gate? It is just like the faucet on your drain in your kitchen, I mean in the sink. You turn it on, water come out, you turn it off, water turn off. That is like a gate, right? But this is not. You don't have a physical gate. All you're doing is just shoot some electromagnetic wave pulse to it, and then it will change. So there are two different type of gates.
Isabella Avellino, please come to the attendance office. Isabella Avellino, please come to the attendance office.
So there are different type of gates, right? Some gates you actually have a classical counterpart, right? So sorry for those who have not learned the classical logic, but classical logic, I think you also deal with it every day, right? I'm going to study if you wash the dishes for me today and also give me $10 allowance for tomorrow, right? That is an AND gate. Both need to be satisfied, right? Or you argue with your parents, whatever they say, you take a negation, right? They say, you cannot go out today, I can't go out today, always this is the NOT gate, right? This the logic happen every day. This gate you find in quantum computer also, which is fine. But quantum computer is important because they have some gate that actually can create a superposition. Right? You give a state 0, it becomes a linear combination of 0 and 1. And you know already why we need this type of gate, because we need to create superposition state so you can harness the power of quantum computer. Right? We won't go to the detail of this so-called broad sphere, but you might see this sphere very often in the literature. Basically, it just say for every state, just now I drawn the 2D plane. 3x plus 4y, and I can rotate that. That is an operation, right? And for quantum gates, you will represent on this broad sphere because it's not a simple space. It is a complex space. Yes.
Wait, so if you measure like an electron inside of its like quote unquote orbit, the alpha and beta are like they're like larger whenever you go closer to like the center of the orbit, right?
Okay. So, good question. So two things. One is that for this broad sphere, we represent the state on its surface. So it should not shrink. Now, you will see people talk about shrinking is because of noise. but we don't talk about that for now, right? So every state, pure state, they will reside on the surface. So just like the Earth, you always reside on the Earth. You don't go into the center. So the alpha and beta will change based on their location on this sphere. Okay, so a lot of things this part, but my main point is that I hope you understand so-called gate is just a microwave pulse or laser pulse. Because remember, quantum computing is a quantum object sitting there, right? A lot of quantum mechanics, which you might not have learned, but you use the laser pulse or microwave pulse to change its state, and that's it. And the state can be mapped to the Bloch sphere, or you can forget about it, but we change the state using the microwave pulse or laser pulse. And that is how to do operation. So here I want to, maybe I just skip this part. I want to talk about, so what is a quantum computer? You start with a state. You can have a quantum computer already if you have an isolated electron floating in the air. Isolated, no noise. It have a certain state. You apply a laser pulse to it with a certain phase angle, you accomplish a certain rotation of the state. I'm not rotating the electron, remember. This is rotating. Electron is in our real 3D space, but what we are rotating is state. For example, I'm still standing here. You say something to me, you influence my mindset. For example, I hate banana yesterday. You keep saying, oh, banana is good, you're good in nutrition. Then I suddenly, my state changed. Oh, I love banana, right? You don't move me, right? Don't laugh. You don't move me. You did not move me in the real 3D space, just like the atom or electron. You don't move in the 3D space. You change its state. So that's an important concept, right? So I keep doing this, but quantum computing is reversible. If I can move it in one direction, the state, I can move it to certain direction, I can move it back. I can move me back so that someone tell me, yeah, I don't like banana again tomorrow, right? So it is reversible. So it's a reversible computing, yeah.
That says flow of time instead of space, so we need to go back in time?
That is a good catch. So first of all, why I have this figure, because you should talk to electrical engineer, they have designed the circuit. In a circuit, they actually will put in different gates. I put a NOT gate here, you really need to put a gate here, NOR gate. And gate, not gate, right? So when they show this gate, it's a flow of the space. You really see that. So what I mean is that you really see it's a space layout. Here I try to say is that I actually don't put a gate. This one is still at the space. But later at time 1, I shoot this pulse. Time 2, I shoot another pulse. That is what I mean by the flow of time in this direction. But you caught one very important thing. Are you saying that I can go back in time? So no, yeah. So then you are the first one to tell me that this what I'm saying is not complete. Very good, yeah. So so definitely I'm not going back in time. What I'm trying to, so this is, yeah. So I should actually have this. So yeah. Until you do the measurement, because once you do the measurement, it collapses. You lose all the information. Okay. This one, I also want to spend some time. It's very interesting. I said that there is no error correction, right? So sometimes we live in noisy environment. You go to a restaurant with your parents, they tell you something you cannot hear. What will you do? Can you say it again? Then they say it again. And let's say your father tell you, okay, you got to visit Uncle Jeff on 10th of this month. Which day? 9. You heard 9. Oh, what? 9 or 10? 10. You ask 10 times, maybe 6 of times is 10. Then you say, okay, I'm pretty sure he's talking about 10, right? Because you use something called majority vote, right? Oh, you keep getting some information, but it's noisy. However, you agree that under some theory, the one you get the most probably is the right answer. This is a kind of error correction already. Or if you try to compare a homework assignment, right? You don't know which one is correct, right? All I've done, I don't know if I'm allowed to do that. Hey, what is the answer, right? Oh, most of us get this B. Then you trust that maybe B is the right answer, right? But you cannot do that in quantum computing, because there's something called no cloning theorem. You cannot copy. So if I want to do that, I may have many identical copy of the electron state I have, but you cannot copy. This is a pretty interesting thing. People did not know about this theorem before 1984 or something. And then someone came up with a very smart idea to transmit information faster than the speed of light. And he published this journal. He submitted to the journal, a very prestigious journal. And then the reviewer and editor know something is wrong, but they cannot figure out why it is wrong. And they say, let's just publish, maybe more people can read and they tell us what is wrong. And because of that publication, we have proved that the wrong assumption is that they assume they can copy the state. But it is very easy, just a few lines, you can prove that you cannot copy the state. There's no way for you to copy a quantum state. Yeah.
Wait, why can't you transmit information faster than like the speed of light using like entanglement?
So entanglement does not really transmit information faster than the speed of light. So like this is just like what I'm talking about the graph, right? I know what's going on, but I'm not transmitting my information to my friend, because you think about that, I need to ship the graph to him for which is very slow already. Yeah, maybe I don't explain this well. Again, I don't understand it well, but it is not transmitting faster than the speed of light.
So it's like if you have the electron here, you have the electron far away, and they're both spinning in some state we don't know, and then I observe it right now. I can see that it's whatever.
Yeah. But
I can see that it's up, right? Then my friend far away doesn't know that that his is also up. Right?
Yeah,
The argument is that if he
Yeah,
does a
sure.
measurement, he find that it's up, then he know that you are up already. But however, you cannot use this to transform any useful information. I try to think about that. For example, can you use this one to change the history of it? This is a good thing, right? So your friend know immediately what you are. But one way you can think is that he even doesn't know you have measured something. How does he know you have measured the electron?
So then the only way for him to know I've measured it is if I tell him.
Yeah.
And then that would have to get the speed of light.
Exactly. That's the main point, right? Because I didn't know he has measured. Yeah, I got 1, but it might be before he has measured, so he might not have 1 or 0 before that, right? Because maybe we just talk to him, hey, if I measure 1, then you do something and make the stock market collapse, then I can benefit from the stock market, right? Faster than other people. But you find out that you cannot. Just think about that. It's a very interesting problem, right? So no cloning theorem, you cannot copy. Then how do you do correction, right? So classically, if I have 0, I just copy many times. And then I just do majority vote. If one of them flip, I still have 2 0. I know my information is 0. But now I cannot copy. By the way, how do you copy something? You actually need to measure it and then copy. Right? Even for all this classical computer, I want to copy a file. What it really does is read your file and then make another copy. But now in measurement, you actually make the state collapse, right? Alpha plus 0 plus beta 1 becomes 0 or 1. You lose the information. That's why you cannot copy. So you will need to come up with very smart idea called quantum error correction circuit, in which you don't really measure it, but you entangle it with an auxiliary bit. And then you measure that bit, you then know what happened. So this is like syndrome measurement, right? In some traditional medicine, they don't really test what virus do you have, or if the doctor is very experienced, maybe just measure your fever, temperature, measure my heart rate, how I breathe, and then the doctor already know that whether I have COVID or just regular fever or regular flu, right? So that does not touch my virus, right? Let's say if you touch the virus just explode and damage the world, for example, right? Now I can do this and then I know what happened to myself, right? So error correction is a very important topic, right? So I'm slow, but I feel that it's necessary to go over those basics. I won't go to all of this hardware, but I will just touch briefly, right? We talk about the ideal case, what a quantum computing algorithm is. How do you implement it? We have talked about electron, talked about other things. For example, electron can have spin up, spin down, then you have a superposition. Spin up, spin down represents 0 and 1. Here is so-called photonic. You shoot one photon, right? The light. When it's small, it become, when it's very weak, it becomes one photon. You have two paths. You shoot into here. You actually don't know which path it goes because they're symmetric. It's a wave. So this is, if you go up, it is called 0. Go down, it's called 1. You never know where it is until you do the measurement. If I measure here, I find the photon, then I know the photon is not here. It collapsed, right? So this is easy to understand. I mean, not easy, easy to visualize, right? There's another qubit, just learn the name called superconducting qubit. This is one of the most promising one. The Google and IBM Rigetti, right? They're all in the Bay Area. They have the quantum computer. Rigetti is in Fremont. You even can consider to find an internship there, right? It's talking about an extra pair of Qubit pairs. We can introduce the physics a little bit. When you cool down a circuit, a metal, to very low temperature, they become superconducting. And they are no longer electrons, they become electron pairs. Okay, so they have what they call Qubit pair. And they use with one extra pair of Qubit pair or without one extra of Qubit pair to represent 0 and 1. Yeah.
Wait, so are they like essentially entangling these two this electron pair together by like making them to like close to absolute 0 levels?
Yes, not entanglement, but yes, you make them very close to it at very low temperature, then they will pair together. Yeah, otherwise they will break at high temperature. Yeah. But anyway, so you see this one, and I want to emphasize is the temperature scale. You see that people use something called dilution refrigerator, right? Which go to as low as 0.01 Kelvin, which is 10 millikelvin, in order to make the qubit energy, qubit words, the transistor, yeah. So maybe this will be my final slides because time's up, but we can, if those want to stay, we can talk more. So what is a quantum computer? It has here is a controller. This is no difference from your microprocessor, your laptop, but more powerful. You do Python programming, and what it does, you just say, okay, send a certain pulse. And then this is the so-called microwave circuit. They will send a pulse at the room temperature nowadays, because we still cannot integrate well. Then they will keep going down to 4 Kelvin, 700 Kelvin, and eventually 10 millikelvin. What it does is no difference from your cell phone. You say something, and you shoot the microwave pulse out. Except that we guide it to the low temperature chamber. In this low temperature chamber, you have some microwave component, and you have a qubit. Just for example, you can put an atom. I just make it simple. It's not atom, it's a superconducting qubit, but it's just a circuit. Just treat it as a quantum object. And then we do the measurement, and then we go through this amplifier. I mean, if you do the manipulation, you're done. You rotate it already, rotate the state. You don't really rotate it in the physical space, okay? Again, just like you change my mind so that I like to eat apple. I'm still standing there, okay? You keep talking to me, then I like apple, like orange today, right? Keep changing the state. But you want to do measurement, right? You also then send a pulse. Now you talk to me, hey, tell me what you like. Then I say, okay, I like orange. But the signal is very weak, you need a lot of amplification, and you measure. All these are classical. Only one of them is what I call the boring passive wave function. If you don't have this active control, your electron just sitting there have its state. Just like I keep thinking I like a certain fruit. And that's it. You're no use to anyone. Until someone tell me that, hey, now you should like orange, whatever, and then do that is the processing of a quantum computer. Okay, I will stop here, but I welcome any questions. I mean, I just want to let you know what I skip is not big deal. It's just go deeper to talk about those how to do the read and then the single qubit gate. But actually, I want to finish this slide, the last slide. So we already say quantum state is very profound. If I have 300 qubit, to describe a state, I have 2 to the power 300 compressed number. No one can handle this, right? But basically it's useless because I cannot read it. So that's why people use some constructive or destructive interference instead of knowing every number, it try to come up with some questions. For example, let's talk about this period of function. You know about the period of a function, right? So how long it will repeat itself. This is very important because all your encryption with the bank is based on finding the period of a certain number. If you can find the period very fast, you can crack all the password immediately. That is a part of the so-called Shor's algorithm. Shor's algorithm is the one that actually triggered the whole community seriously studying quantum computing. Because he came up with that algorithm to show that I can crack it, and then the whole world starts studying quantum computing. Yeah.
Wait, so if you, like, banks use hash functions, right, for passwords and stuff like that, right? So wouldn't there be able to have to be like multiple passwords that you could crack using quantum computing, because hashes aren't like lossless?
I'm not familiar with that, but when we say crack the password, right, it's like you actually try to do something called prime factorization. So if you can factorize it fast, then you can find out all the passwords, because usually they have a public key where you talk to the bank, and then you have private key, right? And the key that's constructed in the way is that you can factorize your private key very fast. So that is how it works, okay? But anyway, what I want to say is that they don't try to find what function it is. They not try to calculate every function. They just calculate the period of the function, okay? Yeah, so finally, quantum computer cannot replace classical computer. Based on what I just said, probably you already realized that you cannot do 1 + 1 in quantum computer. Really, it just doesn't work, right? But it can use to do some very difficult tasks that classical computer cannot solve easily, like optimization. Okay.